Here we're going to determine the magnitude and direction of our resultant vector. So the first example is u plus v, and I already drew those vectors head to tail. So u plus the v joined head to tail gives us a resultant going from the tail of the first to the head of the last. So my resultant vector looks something like that. Now to calculate the magnitude of this, do you see that we have an oblique triangle where we know two sides and the contained angle? That tells us we can use our cosine law that we did back in our trigonometry unit to help us get the magnitude of r. So cosine law is that a squared equals b squared plus c squared minus 2bc cos of angle A. So r squared, our resultant vector squared, will equal 6 squared plus 8 squared. So our two short sides, or two sides between the contained angle, minus 2 times those two side lengths, 2 times 6 times 8, times the cosine of that angle between them, which is 125 degrees. We can throw that into the calculator, get an answer. You're going to get the magnitude of r being approximately equal to 12.5, and it's going to be meters per second. So this is talking about a speed, meters per second. What's the resultant speed going to be when we combine these two things together? I believe the line above that was 155.06 approximately. All right, now we also need that angle at which that vector is acting. So I'll label that angle as a theta. We'll do it in relationship to vector u. If I look at this, I think a sine law is appropriate here. I could take the sine of angle theta and divide that by side across from theta, which is 8, and that's going to equal the sine of 125 degrees divided by that 12.5 meters per second. I'm going to multiply both sides by 8, and then we'll do inverse function sine on that, and that will give us our theta. So we're just timesing by 8 on both sides. That gets rid of it here. Times this side by 8. That's a dot for multiplication, or we can just put it in brackets. That will give me the sine of theta, and then second function sine on that will solve for theta. So theta is approximately equal to 32 degrees there. All right, so our resultant, therefore the resultant is 12.5 meters per second acting at an angle of 32 degrees, and I rounded that answer, of course, 32 degrees to vector u. Okay, or I could have said to the 6 meter per second vector, to vector u. All right, so next one. We have vector u plus vector v. So I've got vector u on the bottom, 40 newtons, vector v heading upwards. The angle between those two vectors is 80 degrees. So remember, we defined the angle between two vectors as being the angles when they're joined tail to tail, what that angle is between them. To be able to add those, I want to pick up vector v and join it to the head of vector u. So I'm going to try and draw vector v. It has to go in the same direction as it is and be roughly the same magnitude. So that was my attempt at drawing vector v to look exactly like the other vector v, which is 10 newtons. My resultant vector then is going to go from the tail of the first to the head of the last. And there we are with our resultant. Again, we could use cosine law here, but right now I don't have any angles in that triangle. However, we have the parallel lines. V is parallel to V because they run the same direction. So if I use that C pattern with parallel lines, I know that the angles inside the C have to add to 180. And since I already know that other piece is 80 degrees, 180 minus the 80 will give me this angle in here, which will be 100 degrees. All right, so we have 100 degrees in here. And now we've got cosine law that will work nicely to find our resultant vector there. So why don't you put the video on pause, see if you can work your way through that. Get the angle also at which it's acting. When I do this, I'm going to find this angle here, acting towards the u, or with respect to the u vector there. Put the video on pause and see what you get there. Okay, working through that one, I got that the resultant was about 42.9 newtons or about 43 newtons, acting at an angle of 13 degrees to the 40 Newton vector, or to vector u. All right, part C is a subtraction of two vectors. So remember, to subtract vectors, we're going to add the opposite. So I still start with u, but then I could add the negative v. So it's v that I have to turn around, not the u. All right, so try that question. Again, put the video on pause, try it, see how you do, and then you can check your solution. Okay, just to set up the diagram, I've changed the direction of v to be the opposite, and I joined it up with the head of vector u. My resultant goes from the tail of vector u to the head of vector negative v. All right, so I also need an angle within that triangle. And to figure that out, again, I've got parallel lines here, so I'm going to trace out my parallel lines, and you see that we have a Z pattern, and by the Z pattern, we know that the angle in the crux of the Z will be equal to each other. So those two angles are equal to each other. That makes that interior angle there a 35 degrees. So we know, whoops, let me use the right pen here. We know that the angle in here is 35 degrees. Okay, so you can use your cosine law with that still. We still know the magnitude of vector v is 60 degrees. Or sorry, 60 kilometers per hour, not degrees. Kilometers per hour. So again, cosine law makes sense for our resultant magnitude. Sine law, again, to get our angle. All right, check your work with that. I got that the resultant is 46.2 kilometers per hour, acting at an angle of 48 degrees to the 80 kilometer per hour vector. All right, example number 2 here, a force of 60 newtons with a quadrant bearing of north 52 degrees west, which we talked about in the previous lesson, added with another force has a resultant of 75 newtons with a quadrant bearing of south 85 degrees west. Calculate the magnitude and direction of the unknown force. Okay, so we have force 1, we would add force 2, and then we get our resultant piece here. So let's put this on our quadrant bearing plane here, or the compass rose. So I've got my north, east, south, and west. And our force, I'm going to call this F1, force 1, is 60 newtons with a quadrant bearing of north, but I'm veering off 52 degrees towards the west. So let me do that in a different color from our compass. I'll do that in blue, 52 degrees towards the west off of north. So this angle in here is your 52 degrees. And that has a measurement of 60 newtons. So that's our first force. To that we would add a force, and then the resultant is going to be our 75 newtons. Its quadrant bearing is south 85 degrees towards the west. So it's like super close to the west. Okay, and this angle in here is our 85 degree angle. Okay, so south, but veer to 85 degrees towards the west. And that one has a magnitude of 75 newtons. What we need to figure out is our force 2, what we're adding to force 1. So force 2 would join from the head of that first vector to the head of the resultant. So if you think of your force 1 here, force 1, I should have done that in blue, force 2 would have had to go along here, so put force 2 here. And that one, when added to force 1, gives us that red vector, which is our resultant vector there. All right, so that makes sense in terms of the diagrams that we've done so far. So we just need to solve for that one. So we're going to need, see the triangle there, we're going to need an angle in there, and then we can probably calculate our magnitude because we'll have two sides and an angle, so that will get us there. Now, what I know is I've got a straight line, the north-south is a straight line. I have two components, the blue angle is 52 degrees, the red angle is 85. The one in between the red and the blue vector, my resultant in my force 1 vector, that value would have to add to the 52 and the 85 to make 180, so we can calculate that one. Okay, so we've got that interior angle there of 43 degrees. Now we can use cosine law to calculate the resultant vector, the magnitude of the resultant vector, or not the resultant vector, I should say force 2 vector, not resultant. Once we get that, we also then need to get its direction, which I'm going to tell you, I'm going to work with the angle up here. I'm going to solve for that angle, but then I'm going to do something funky with it. So why don't you give that a try, see how you get along with that. If you think you know how to come up with the actual quadrant bearing, its direction, because all the other ones are based on quadrant bearings, we need to be consistent, then go ahead and do that. If not, but be sure to listen to the rest of the video. Okay, I found the magnitude of my force 2 was 51.4 newtons, and then I solved for that angle up in the top, which is 84 degrees. Now that is not yet a quadrant bearing, but we're going to make it into a quadrant bearing. What I'm going to do is superimpose a north, east, south, west, a compass rose that's going to lie like this through that vertex, through that, that spot there. The reason I'm doing that is because then I've got alternate angles that I can work with, and it's actually going to be pretty slick here. You just watch. You might be amazed. What I have is north heading straight up and down. I'm going to trace out vector F1, and then I'm going to trace down my south that I just put in there. That's a Z pattern. And based on that Z pattern, then I know, since I've got a 52-degree angle in the crook between F1 and north, that was 52 degrees. That means by the Z pattern, this piece here is 52 right in there. Now that entire angle had to add up to be an 84 degrees. So if I look at where my south is heading straight down, my force 2 is coming off of that. I can take my 84, subtract the 52, and that gives me how many degrees to the west of south that force is being applied. So we have 84. We're going to take off the 52 degrees, and that's going to leave us with 32 degrees. So that is equivalent then, the direction for that would be south 32 degrees towards the west. So therefore the resultant, or not the resultant, I keep saying that because we were doing so much with resultant on the previous ones, the force 2, the second force, or the other force, there we go, oops, I keep hitting my undo, there we go, the other force has a magnitude of about 51 newtons, 51.4 newtons, and a bearing, quadrant bearing or direction of south 32 degrees west. And there you have it.